Well, you're good to go.
All right. Well, welcome back to discussion, everyone, for CS 2100. Peter's out today, so I'll be teaching this section today. This is it. This is the last lab section, or the last discussion section of the entire class. Kind of crazy to think about. We made it this far. And yeah, today we'll mostly be focusing on graphs, as well as maybe a little bit of combinatorics review in preparation for the upcoming final. Anyone have any questions before we get started?
Looks like someone still doesn't see the slides. They should be under week 14.
Oh, it says she sees them now.
Okay, cool.
Okay, cool. So we should be good. So, no one has any questions. I think we'll get right into the questions. So, prove that for a simple graph G, in which all the n nodes have a degree of at least 2, there are at least n edges. And I'll give you guys 2 to 3 minutes to think about this one, and then we'll talk about it. All right. So let's talk about this problem. So we have a simple graph G. All nodes have degree of at least 2, and there's at least n edges. Or so we want to prove that there's at least n edges. So this one's what we want to prove. And then all this other stuff is what we know. So let's first quantify what we know. Or let's talk about what we know. What do we know that, or what does it mean that the graph is simple? Well, if the graph is simple, it means we have no self loops. Then it also means we have no double edges. And we also know that every node has degree of at least 2. So for every node, there's at least 2 edges coming from that node, right? So the first piece of information that might be useful is, how do the number of edges relate to the sum of degrees in the graph? Well, we know that for every edge in the graph, there's 2 nodes connected to that edge. So let S be the sum of degrees in all the nodes. How do we write S in terms of E? What the hell? That was awkward. No idea where that came from. Okay, let's see. So, let's see here. So how does the number of edges relate to the number of vertices in the graph? All right, so we know that for every edge, we add 2 to the sum of all the vertices. So S, the sum of the degrees of vertices, equals the number of edges divided by 2. Or no, equals 2 times the number of edges. So sum of all degrees of the vertices equals 2 times the number of edges, right? So if we know that the degree is at least 2n, so we know that the degree of the graph is greater than 2n, or the sum of all the degrees is greater than 2n. So 2n equals the sum for every vertex element of the set of vertex, degree of that vertex, equals what? 2 times the number of edges. So that also tells us that n, assuming that there are exactly 2n vertices, n equals the number of edges in our graph. And this proof is easily generalized to show that there must be greater than or equal to n edges in the graph, right? So now assuming that 2n is greater than or equal to e, 2e, it's easy to show that n must be greater than or equal to e. Anyone have any questions about this one? Does this make sense to everyone? All right, awesome. Any questions about this one before we move on? All right, great. Okay, so here's a question on representing graphs, or on representing relations as graphs, and then adjacency matrices for those graphs. So I'll give you guys 1 or 2 minutes to work on this one. Really, we just want to represent this relation as a graph, and that graph is represented by an adjacency matrix. I'll give you guys 1 or 2 minutes to think about this one, and then we'll talk about it. All right. So since I want to make sure we get to some of the tougher problems, I want to start on this one real quick. So we have our adjacency matrix. We got vertices 1 to 4 on the side, and we got vertices 1 to 4 on the top. So position I comma j on this matrix equals 1 if ij is an element of our relation, right? So our graph is going to look something like this. We have 1, 2, 3, 4. 1 relates to itself. 2 relates to 3. 3 relates to 2. 4 relates to 1. And then 4 also relates to itself. So how do we fill in the adjacency matrix? Well, it's a 1 if there's an edge from whatever's on this column to whatever's on this top row, right? So 1 only relates to itself. 2 relates to 3. 3 relates to only 2. And then 4 relates to itself, and then it also actually relates to 1 as well. So now we have an adjacency matrix representing our graph. This one should be pretty straightforward. Anyone have any questions about this one? All right, I guess we'll move on to the next question then. All right, so here's another proof about graphs. So prove that if U and V are vertices in a graph and that there's a walk between them, that there's a path between them. And I'll give you guys 2 to 3 minutes to think about this one, and then we'll talk about it. All right, so let's kind of talk about this one. So what do we know? We know that U is some vertex in our graph, as is V, and we know that there's a walk between them. And we want to prove that there's a path between them. So what's the difference between a path and a walk? What can walks have that paths can't? From Miles in the chat, path has no repeated vertices. Correct. I would agree with that. So if there's a walk from U to V, we might have something that looks like this. We start on U, then we go to edge 1, then maybe we go to vertex A, then maybe to edge 2, and then to vertex B, and then to edge 3. And it's possible, since vertices are repeated, that maybe we go back to U. And then maybe we go to edge 4, and then C, and then edge 5, and then D, and then edge 6, and then maybe we go back to C again, and then edge 7, all the way to V. So this is a walk from U to V. So how do we prove that any walk from U to V can be turned into a path from U to V? We have to get rid of all the repeated vertices if we want to turn this into a path, right? But how do we know the path will still go to V? How do we show that if there's a walk from U to V, then there's a path?
Doesn't the book have a proposition that essentially says if there's a walk, then there's a path? Somewhere
Okay.
in it?
Probably, because it's true, right? It's probably a theorem in our book. Let's say we don't have a theorem. How do we prove that theorem? Or maybe even intuitively, why is this the case? Why is there always a path if there's a walk?
Well, if we repeated a vertex, then we kind of went in a circle. So if we just removed the circle, then it should still be valid to go forward.
Great. Yeah, no, completely agree. If we're repeating vertices in our walk, we're literally going in circles. And we know going in circles is pointless, right? So this thing right here is a circle. We can just get rid of all of that, right? We completely got rid of the repeated vertex. So basically, if we ever see a vertex twice, we basically remove everything in between, right? Or all that useless work we did. We literally went in a circle here, so we can just delete that. We also go in a circle right here, so we can delete all of that. And what we're left for this particular walk is a path from U to E4 to C to E7 to V. And this is pretty easy to generalize, right? That we can take any walk, we can get rid of all the circles, and we still end up at the same place, and we don't repeat any vertices. So if there's a walk from U to V, there must be a path from U to V. Everyone agree with that? All right, great. If there are no questions, I think we'll move on to the next problem. So prove the following statement. Let G be a bipartite graph. Prove that every cycle in G has even length. Real quick, I wanted to remind everyone what a bipartite graph is. Can anyone tell me, first of all, what a bipartite graph is?
Do you mind if I speak?
Yeah, of course.
A bipartite graph, if I remember correctly, it is a graph that you could like split into two sets, and every edge connects one set to the one of the other set. And
Right.
so they're always whenever you go through an edge, you're switching sets. So it's always
right. So
Yeah.
a bipartite graph is a graph that's separable into two sets of vertices. We can call them V1 and V2. They look something like this. The idea is that in a single set of vertices, no vertex has an edge to another vertex in its own set. So this is a valid bipartite graph. This graph with no edges is also a valid bipartite graph. And a complete bipartite graph has all possible edges. And it would look like this in this example. So now that we kind of know what the definition of a bipartite graph is, if a graph is bipartite, how do we prove that every cycle has an even length? I'll give you guys 2 minutes to think about it, and then we'll talk about it. All right, so let's talk about this. We know that we have a graph. It looks something like this. How do we prove, knowing that G is bipartite, that every cycle has an even length? Anyone want to maybe take a shot at it or share their approach?
I'm thinking that whatever vertex you start with, any edge you traverse, you're going to end up in the other thing. And to get back to the original vertex that you started with is always going to be even, because each edge traversal takes you to the other set. And so to get back to whatever set you started in is always going to be even. And the vertex you started in is in the set you started in. Something like that, but more eloquent. You're muted, Ombre.
All right, yeah, great. Agreed. So yeah, it's good logic. So let's think about this, right? Let's show how, using that line of reasoning, that if there was an odd cycle in this graph, that we might end up in a contradiction or something, right? So we know that every cycle in our graph is going to be some sequence of vertices that looks like this: v1, v2, v3, etc. But we know by definition of bipartite graph that they're going to alternate sets, right? So this first one is in set v1, first one's in set 1, second one's in set 2, third one's in set 1, second one's in set 2, and etc. So let set 1 be the set of vertex 1, right? And so we'll do this all the way out to vertex n. So let's assume that our graph is bipartite and that we have some odd cycle starting with vertex 1, ending on vertex n, right? Where n is odd. N is odd. Well, what does that mean? It means the last vertex in our cycle is going to be in group 1. The first one's in group 1, though. Why are they both in group 1? Because if G is bipartite, we have to alternate vertices or the groups have to alternate in our cycle. That's by definition of bipartite graph. And then by definition of cycle, there must be an edge between the last vertex in the cycle and the first one. But we see if that cycle's odd, then now we have an edge between two vertices that are in group 1. So what does that mean? Because again, if our graph is bipartite, our cycle has to alternate groups. 1, 2, 1, 2, 1, 1, right? What happens, right? Well, our assumption that we have an odd cycle in a bipartite graph just led to a contradiction. There's an edge between two vertices that are both in group 1, which means the graph is not bipartite. But wait, it was bipartite. The graph is both bipartite and it's not bipartite, right? Which is a pretty clear contradiction, right? Thus, no cycle in a graph can be odd. And since every cycle in a graph must be either even or odd, then all cycles in our bipartite graph must be even. Does that make sense to everyone? All right, awesome. So again, we assumed we had a cycle, an odd cycle in a bipartite graph. We showed that that assumption would lead to a contradiction. I want to talk a little bit more about bipartite graphs, since this was the only problem we have on bipartite graphs in the slides, and they definitely could come up on the final. It's possible, right? So a few things about bipartite graphs. Again, they're separable into two sets that look like this. A complete bipartite graph has all possible edges. So something that would look like that would be a complete bipartite graph. How do we know how many edges are in a complete bipartite graph? So maybe this is set V1 and then this is set V2. Well, the number of edges in a complete bipartite graph is going to be the cardinality of set V1 times the cardinality of set V2. And this should be intuitive, because for every vertex in group V1, there has to be an edge to each vertex in group V2. And that is just multiplication. So if we want to know how many edges are in a complete bipartite graph, you multiply the cardinality of the two sets together. Bipartite graphs, and this may seem like a little bit abstract or theoretical, although I will mention that it's a little bit more useful than you might think. There's actually a lot of problems in the real world we can solve using bipartite graphs. And the last thing I'll say, since this is our last graph problem on the slides, and I do want to talk a little bit more about this because I think it'll be really useful to you guys. I had an interview for a software engineering internship for a really well-known company, very well-known company. Most of you guys would probably know who they are. I really can't say because they'll go after me for disclosing interview questions. But this is the question they asked me, and the answer actually relates quite a bit to bipartite graphs. So you're given a list of people, say P1, P2, P3. Basically, you have n people, right? So this is like for n equals 4. You have n people. For each person, you're given a list of people that like they don't get along with, or like people they don't like, right? So if P3 is in P1's list, it means that P1 and P3 don't get along. Similarly, maybe P4 is in P2's list. And then maybe P1 is in P2's list as well, right? So the interpretation of that is that person 4 and person 2 don't get along, and person 1 and person 2 don't get along. How do you solve this problem? So we're given a problem now that you have to separate all of these people into two different groups such that everyone in the same group gets along. How do you solve this problem? And the answer relates really closely to bipartite graphs. Anyone have any ideas of how you'd solve this problem? Okay, let's start here. Let's represent each person. Stop hiring such fussy people. Agreed. But let's say people are fussy anyways. How do we separate them into the two groups? Well, let's see what happens if we represent each person as a vertex in a graph. And now for everyone on each person's list that they don't get along with, let's just have an undirected edge from person or between those people. And the reason I choose undirected edges here, is because if person 1 doesn't like person 3, then person 3 can't be in person 1's group either. And we're trying to separate these guys into two groups where everyone gets along, right? So this edge between P1 and P3 means we can't put them in the same group. P2 would have an edge to P4 and to P1. Now we have a graph. What property about this graph will tell us whether or not we can separate them into two groups like this?
If it's bipartite or not?
Exactly. If the graph is bipartite. So for this particular graph, is it bipartite or not?
Yes.
It is bipartite because we can separate them like this. Maybe P1 is in this group, which means that P2 and P3 must be in this group. And then we can have P4 in this group. So this problem has a solution if and only if the graph is bipartite. The interviewer was kind of surprised how quickly I gave them the answer, probably because I've TA'd this class before. I guess what I mean to say is that, yeah, Alec, I did actually get the offer, which is pretty cool. I turned it down for another company. But yeah, thank you. I appreciate that. More of the story is that graph theory, while it might seem really abstract, it's got a lot of real world applications. Really, when we have anything, right, any objects in the world, people, maybe intersections, etc., if we can represent relations between them, we all of a sudden have a graph, right? So graph theory, we can use it to solve a lot of interesting problems, including this one. So even though it may seem pretty theoretical, I guess what I mean to emphasize is that a lot of this stuff is pretty useful in the real world for problem solving. And it will come up a lot more in the major and probably on the upcoming test as well. And for anyone curious, you can check if a graph is bipartite in order V plus E time. And you do this with a modified DFS or BFS. And I encourage all of you to go try to solve this problem on your own. It's a pretty fun problem, pretty interesting problem. Because I do want to get to the next problem on the slides. I won't talk about how this would be done in order V plus E time, but it's pretty intuitive. And yeah, again, I encourage you guys to go try and solve that problem. All right. This was the last graph problem on the slides. Although I do want to review some combinatorics as well. So this was from one of the quizzes in one of the previous years about combinatorics. So basically, how many different ways are there to form 7-digit strings having no zeros where we only distinguish between the number of appearances of each digit, right? So these strings are both the same. These ones are not. So a better way to rephrase this problem is how many unique multisets are there from the digits 1 through 9? So a multiset is just a set where we can have multiple of the same item, but order doesn't matter, right? So 777555 and 5557777 represent the same multiset. It's like a basket problem. Yeah, agreed. It is like a basket problem, right? We need to create a multiset from a list of items 1 through 9. So maybe we have some bag or some basket, right, that's full of digits 1 through 9. We can choose as many as we want, right? And we want to choose 7 items. And order doesn't matter, right? The set 7777555 and 5557777 are the same. Order doesn't matter. How many ways are there for us to choose multisets like this? How many unique multisets are there? This is probably the hardest topic we've talked about in combinatorics in this class, in my opinion. Anybody remember how to solve problems like this? It's combinations, but repetition is allowed. So we want to choose 7 items, but if we want, we can repeat, right? So we have 9 digits. We want to choose 7 from those 9 digits, but we're allowed to repeat digits. Does anyone remember how to solve these? So I will remind you guys of the formula, but then I'll actually talk about the intuition and why the answer is what it is. So for problems like this, where you want to choose R from a set of n items where repetition is allowed, would be n plus R minus 1, choose R. So in this case, the answer to this problem would be 15, choose 7. And I'll emphasize that that equals same thing as 15, choose 8. Choose 8 is exactly the answer to this problem. But why? Why is the answer to this problem choosing 7 from a group of 9 with repetition allowed? 15, choose 8. Well, let's think about it. Instead of 7 slots, we have 15 of them. 11, 12, 13, 14, 15. Now let's take a look at an example solution where we choose 8. Maybe we choose that one. 2, 3, 4, 5, 6, 7, 8. Somehow, this represents a solution to our problem. So how does this represent one of our unique multisets? We chose 8 out of 15. How does this represent one of our multisets? Why is this 8 out of 15 one of the solutions to our problem, right? This represents a string that looks like this. It's some multiset of the integers 1 through 9. This is one of our possible combinations that we want to count. And if we count all of them, again, it's this 15 choose 8, which is the same as this 15 choose 7. Well, so let's think about what these check marks represent. We chose 8. Why did we choose 8? Why do we choose 8? It's got to mean something if it solves this problem, right? So let's imagine that every green check mark, each of these 8 that we just chose, imagine that it's a divider. And it's a divider between 2 of the different types of items, right? So maybe everything before the first divider, maybe these are all 1s. Everything after the first divider, those are all 2s. The same logic applies for the other dividers. And there we go. By choosing 8 dividers in a set of 15, we're left with 7 slots left over. And those 7 slots represent exactly a way that we can create a multi-set from the 9 items in our bag. In this case, the sequence that we represent is this: 1, 1, 2, 3, 4, 4, 6. And with this same logic of choosing dividers in some greater set, we can count all the possible multi-sets, which is 15 choose 8. Does this make sense to everyone? So let's say maybe I move some of these dividers around. Maybe we choose another 8. Maybe we choose this one, this one, this one, this one, and then maybe these 4 at the end as well. But what does this mean? What multi-set does this combination represent? Well, anything before the first divider is 1, anything after it is 2, after the second divider is 3, after the third is 4. So after the fourth divider, we have all 5s. So this is another one of our unique multi-sets. And again, by this logic, we count another one of our unique multi-sets. So we took this problem of having a bag full of 1 through 9 and having to choose 7 of them. We took this problem, choosing from a bag with repetition allowed, and we simplified it into a problem we already know how to solve. Is choosing 8 out of a set of 15 with no repetition allowed. So just by looking at this problem a little bit differently, we can view it as a problem that we already know how to solve. And that's why our solution to this problem is 15 choose 8, which is equivalently 15 choose 7. Does that make sense to everyone? All right. So using that same logic, let's move down to problem B. Does anyone have any questions about A before we start this? All right. So problem B. So same problem above, but now there's a constraint that each instance can have no more than 2 sevens. So how I would recommend solving this problem is count how many combinations there are that have at least 3 sevens, and then subtract them out of the total set. and I'll give you guys 2 to 3 minutes to think about this one, and then we'll talk about it. I'll be right back.
And then this discussion gets done at 1:45, so we might just want to wrap up this.
All right. Yeah. Sounds good. So if anyone wants to stay around for the solution to this problem, feel free to. But yeah, this has been the final discussion section for 2100. So with that said, good luck on the final, guys, and have a good day. You're all free to go. If you want to stick around for the solution to this problem, feel free to stick around. All right. So again. All right. Miles. Okay. Yo, Miles, you're still there, right?
Yes.
All right, great.
No.
Congrats. You're the only one that stayed to find out the answer to this problem. So, do you have any approach to this problem?
Not exactly. Yeah, I was kind of just wanting to see how it happened, I guess, so I could learn from
yeah.
it. But
So think about it. So we calculated in the last. Answer, problem A, that there are 15 choose 8 total possibilities, right? And now we want to subtract out the ones that are unfavorable. So the ones we want to subtract out are the ones that have at least 3 sevens, right? So let's say, again, we're choosing multi-sets, right? We require that there are already 3 sevens.
okay, yeah, that makes sense.
So now what does this mean? It means we have to choose 4 more. So it's really the same problem above, only you're choosing 4 instead of 7. So how do we solve the problem? So we can honestly just ignore this fact that we already have 3 sevens. The question at this point is how many ways are there to choose these 4 more slots, right?
Right, yeah.
So it's kind of the same logic above, right? We have 4 items we want to choose, then we have 8 possible slots for dividers, right?
Right,
This is
yeah.
again the n plus r minus 1 choose r. So how many of these unfavorable outcomes are there? How many ways can we fill these other 4 slots?
12, choose 4?
Right. Exactly.
Okay, sweet.
12 choose 4 equals 12 choose 8, right? And the interpretation is that 8 of these 12 slots have to be dividers, right?
Right, yeah, okay. Oh, I see, yeah, this makes
So
sense.
like kind of the interpretation of this is that we choose 2 more ones, another 2, 3, 4, 5, 6, and then another 6, right? we count all the possible ways you can do that. And that's how many unfavorable outcomes there are. So our answer is going to be this 15 choose 8 minus 12 choose 8. And the rest of the calculations are pretty trivial at that point.
Gotcha. Okay, that makes a lot of sense.
All right. Have a good day, man. Good luck.